Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Azra Abdul Rahman. So this is the third topic that I'm going to cover for the course MMFD 5043 Robotics and Automation. And this topic is related to the discrete process control using programmable logic controller. So the content for lecture for this topic is starting with the introduction, then continue with the introduction to discrete process control. And after that, we're going to take a look at the PLC set. And we're going to learn a little bit about programming of the PLC before we summarize with some summary. Okay, let's start with the introduction. If we can take a look at typical automated assembly or manufacturing process, we can see that the components consist of sensors, actuators, PLC, human machine interface, limit switches, drive like a motor, consist of encoder, and also some vision system, and also some safety. So we know that from previous lecture or previous topics, we have a 4 building block of automation, which is sensor, actuator, controller, and communication. We know that control system is a device or set of structure designed to manage, command, direct, or regulate the behavior of the device or a system. The entire control system can be viewed as a multi-variable process that has a number of input and output that can affect the behavior of the process. In the industrial world, the word process refers to an interacting set of operations that lead to the manufacture or development of some products. So in here, the word control is used to describe the steps necessary to ensure that the regular condition produce the correct properties in the product. Let's take a look at what is discrete process control. So manufacturing operations are divided into two major categories. One is a discrete manufacturing, which is concerned with assembly of product. And the next one is continuous process, which is concerned primarily with the blending of formula. Okay, discrete process control deal with operate on parameters and variables that change at discrete moments in time. It might be required to control a sequence of events, maintain some variable constant, or follow some prescribed change. The term discrete state expresses that each event in the sequence can be described by specifying the condition of all operating units of the process. Such condition description are presented by expressions such as valve A is open, valve B is closed, conveyor C is on, limit switch is closed, and so on. A particular set of conditions is described as a discrete state of the whole system. Let's take a look at a simplification of discrete state process control. Let us suppose that all measurement, the input variables, we can take a look at this process. So this process were measured by input variable S1, S2, S3. So it goes to controller, and all control output variables C1, C2, and C3, but the process can take on or be assigned only two values. For example, valve are open or close, either open or close, so two values. Motor are on or off, two values. Temperature is high or low, two values. Limit switches are open or closed, and so on. Discrete state process control is a particular sequence of events through which the process accomplishes some objective. So the term input and output, depending on the variables, measurement variables that go into controller or going out from the controller. Input is depending on the measurement variable that goes into controller. Meanwhile, for the output is the measurement variable that coming out from the controller. So in this case, this example, discrete control, the variable level and offsetting are discrete because they can take only two values. This means that the valve can only be open or closed. And the level is either above or below the specific value. Now the objective is to fill the tank to a certain level with no outflow. To do this, we specify an event sequence, close the output valve, and then open the input valve and let the tank fill the desired level as indicated by a simple switch. And then after you reach the limit switch, then close the input valve. This also some discrete process control example in manufacturing. We have a control system for automatic drilling machine. Might be required to start lowering the drill when the workpiece is in position. So there's a switch, 1, 2, 3, switch contact open when drill reach the surface, switch contact open when drill reach required depth, switch contact close when workpiece in position. So we have a workpiece, we have a drill. So the switch is detecting the presence of workpiece, detecting the reach depth, and also detecting when the drill reach the surface of workpiece then. Okay. So first might be required to start lowering the drill. So the movement of the drill, start drilling when the drill reach the workpiece, whenever it's moved, and then the drill bit touch the workpiece, it will start drilling, and it will stop drilling whenever it reach the required depth. After that, the drill will retract, and then the switch off and wait for the next workpiece to put in position before repeating the process. Okay, so you can see that it's discrete process, and all the input so output has two values. So we can say that the discrete process control, all the parameters and variables are discrete, usually binary, 0 or 1, off or on, open or close. For example, sensor, we have a limit switch, contact, no contact, photo detector on off, timer on off, motor, which is actuator, valve clutch on off, open close, or engage no engagement. So for the component of discrete process control, it consists of two components. The first one is logic control, which is based on the event-driven changes. The next one is sequencing, time-driven changes. We're going to take a look each of these components then. Okay. So first we take a look at the logic control. Logic control is a switching system whose output at any moment is determined exclusively by the value of input. The logic control do not have memory. They have no operating characteristic that depend on time. And this logic control also called combinational logic control. The basic element of the logic control is AND, OR, and NOT. So for the AND logic gate, output is going to be 1 if all input is going to be 1. For the OR logic gate, output is going to be 1 if any input equal to 1. Meanwhile, for the NOT, output equal to 1 if input equal to 0, and vice versa. Additional element based on this basic element of the gates, we can have NAND, combination of AND and NOT, and also NOR, combination of OR and NOT. Okay. When we learn about logic control, we need to know also the Boolean algebra and also truth table. The logic element form the foundation for specific algebra that was developed around 1847 by a person called George Boole, is Boolean algebra. Original purpose was to provide a symbolic means of testing whether complex statements of logic were true or false. However, it's shown to be useful in digital logic systems. In Boolean algebra, a variable is a symbol used to represent an action, a condition, or data. A single variable can only have value of 1 or 0. The table used to represent the Boolean expression for logic gate function is commonly called a truth table. The logic gate truth table shows each possible input combination to the gate or circuit with a resultant output depending upon the combination of this input. So let's take a look at the all the basic gates, basic logic, and also the additional logic. Then we start with the AND gate. The AND gate is representing like a series of electrical connection, which is they have a two switch, two input, and one output, which is the light, and these switches is connected in series. So you can see that whenever the both input is 1, then we're going to have a 1 output. For the OR gate, it's somehow similar to the connection of switches in parallel. So when either one of these switches is on or both are on, then we're going to have the output of 1. For the NOT gate, we're going to have the opposite value. If the input is 0, then we're going to have the output is 1. If the input is 1, then we're going to have the output is 0. So you can see that in order to represent the logical gates, they have some symbol. Commonly, we are using the symbol provided by US, and also some of the symbol we can use also simple. Okay, so this symbol for AND gate, OR gate, NOT gate, and NAND gate, and NOR gate. You have already taken a look at the truth table for AND, OR, and NOT. Maybe you can try by yourself to draw your own truth table for NAND and also for NOR. There's also Boolean algebra. It's good for you to know a little bit about Boolean algebra, even though in this particular course, we're not going to elaborate more on Boolean algebra, but in order to draw some logic, it's good that we know which law can we use in order to simplify the logic. So this is some interactive exercise. You can try by yourself, and if you need some confirmation, you can send it to me, and I can give you the right answer. Okay, this is also some interactive exercise. Try by yourself. It's good for you to refresh this kind of knowledge. Okay, this is some exercise also for you to develop a logic network based on the Boolean expression. Before this, you have a logic network, and then you have to draw the truth table. But now, based on the Boolean expression, you have to come up with the logic network. You can try by yourself. As again, you can send me the answer for me to check or for me to give a solution. That anyhow, you can also search in the internet if you would like to have the answer. If there's some website that providing this kind of question. Okay, this is also some interactive exercise. So if we have a live session, normally I will ask you to do it by yourself, and then we discuss after that. But right now, since it's a recorded video, I really like you to try by yourself, and then you can check with me your solution. And there's also interactive exercise 4, interactive exercise 5, interactive exercise 6. This. Then we move to the sequencing. Remember, there are two components for the discrete process control. So first one is logic gate, logic control. The second one is sequencing. So for the sequencing, it's a switching system that uses internal timing devices to determine when to initiate changes in output variables. Output are usually generated open loop, no feedback that control function is executed. Sequence of output signal is usually cyclical, as in high production work cycle. The signal occur in the same repeated pattern with each regular cycle. Common sequencing device is a timer and also a counter. Timer is an output switch on and off based on a preset time, while counter count electrical paths and store that information. This somehow is sequencing. So if we have a sequence process, then it's based on time, example like a traffic light. So this process is controlled by using the sequencing procedure. Okay, let's move to the PLC. Okay, we can take a look at the control architecture of a drill machine that we have seen before in the previous slides. So for the automatic drilling machine, we could wire up electrical circuit in which the closing or opening of switches would result in motor being switched on or valve being actuated. You can see from this example, there are 3 switches, which means there are 3 inputs. And then there are 2 output, which is the cylinder to move the drill down and up, and also the motor that rotates the drill bit. So in order to do to make system automated, you need to make a connection between all the switches and also these 2 output. Thus, as a result, we might have a switch closing or opening contact, which in turn switch on the current to a motor and cause the drill to rotate. Another switch might be used to activate the current to a pneumatic or hydraulic valve, which result in pressure being switched to drive a piston in the cylinder and so result in the workpiece being pushed into the required position. Such electrical circuit would have to be specific to the automatic drilling machine. For controlling the number of items, we could likewise wire up electrical circuit involving sensors. So you can see that all these input and output need to be wired, connected in order to make the system working as what we desired. So in order to do that, the basic architecture, the basic control system that we can develop is by using relay control system. Relay control system are hardwired system. When a current is switched on to flow to the relay solenoid, normally close contact open and normally open contact close. This contact can use to give control in the system. So we can use several relay in order to perform automated process for the drilling machine. Let's take a look at this video for a while. So this is some introduction of the relay. So you can see that how relays function. There are two circuit. First one is with the coil, another one with the contact, the system. So this is one circuit, the circuit that we would like to control, and this is the circuit that we use to energize or deactivate this coil. So if we power this coil, then this coil is going to have a magnetic field. Then it's going to attract the mobile ion armature, and this will make the contact touch. Then the bulb will turn on. We disconnect this first circuit that is going to contact this relay. So the upper scheme relay, you can see from here the coil and also the contact. Right. So you can see that the example of relay control systems. If we have a relay, have a push button start, stop. This relay somehow we latch this relay, then the relay will connect to the solenoid valve. Whenever we press this push button start, the relay will energize. Whenever the relay is energized, then the solenoid valve will be energized. The second example of the relay control system, we have one relay and then we have two output, red light, green light. We have the similar push and stop button. Whenever we didn't press any, we do not press any start button, by default, it's we start or we switch on the system, the relay will normally open. So the normally close contact will adjust the red light. So by default, the red light will light up. If you press the start button, the relay will energize and then it will make the red light off and it will light up the green light. Okay, and this is another example. If you would like to control a solenoid, two solenoid that controlling the cylinder, you can see that there's several numbers of relay that we are going to use. So for this simple process, we already need three relay. Relay is K1, K2, and K3. Okay, that's the relay that we use in order to control one solenoid. Sorry, two solenoid with a one cylinder. So you can imagine if we have a state-of-the-art factory, how many solenoid valve, pneumatic cylinder, motor, and on-off power switch are required to be controlled just for one machine. Then add on all the necessary control relays. What you get is, yes, machine control, but you also get a logistical nightmare. Why I say that? Because you can have control system, hardwired relay system, which connected to one another, and then it's really difficult if you have an issue, if you would like to troubleshoot, also if you would like to redo the entire system. Due to this problem, then in 1968, a group of researchers or inventors introduced PLC, which is a programmable logic controller. So, what triggered Big Molly and the team to produce PLC is there's some uh, competition introduced by General Motors, and by stated all these requirements, then this team of Big Molly introduced PLC 1st January 1960. You can see that how big is the first PLC compared to the PLC that we have right now. A PLC is a digitally operating electronic apparatus which use programming memory for the internal storage of instruction for implementing specific functions such as logic, sequencing, timing, counting, and arithmetic control through digital or analog modules. Implements logic control function by means of a program, and also can be effectively used in application ranging from simple control to complex function programs. So you remember that discrete process control consists of two components, logic control and sequencing, and these two components can be handled by PLC. That's why PLC is really suitable to be used as a controller for discrete process control. So the PLC is a real-time system, a digital controller designed for multiple input and output, and also immune to electrical noise, vibration, and impact. So if we have a simple system like a switch, you can use PLC, which in as an input, and then the output will be the one. So some history of the PLC or the evolution of PLC. Take a look at first it was introduced in 1968. After that, there's a company called Allen Bradley introduced PLC family, 1774 PS family, and Dick Molly and the team set up a company and then introduced their own PLC model, which is Medicon 184 model. And at the beginning, most of the PLC are produced by the Allen Bradley and also Medicon company. After that, in I would say 1980s, the involvement of Siemens take place. And so Siemens introduced Semantic S5 PLC, and it will go through. And right now, you can see that PLC getting smaller. They have a lot more function than before that. Advantages of PLC: it's reliable, it's a cost-effective, fast operation, flexible, small in size, easy to maintain, require less energy, able to communicate with computer system. So programming a PLC is easier than wiring a relay conventional. PLC can be reprogrammed. PLC take less floor space, greater reliability, easy maintenance. PLC can be connected to a computer system because we would like to make a connection between the remember the information level, control level with a higher level. So by using PLC, it's easy for us to communicate from the device control level to the control level itself. Then PLC can perform greater variety of control function. Some drawback of the PLC: cost and added modules, fixed circuit operation, and also closed architecture based on manufacturer. So you know that PLC have several types of PLC, several brands of PLC. So the architecture of each PLC is depend really on the manufacturer itself. Even though they have some standardization, but there's some element difference the PLC based on their brands. So this example of application, there's much more. Some of it is food processing, car park, manufacturing system, traffic light, optic system, and also conveyor system. I also really like to present the difference between the control PLC with the control relay in terms of control logic changes, deployment on different systems, feature expansion, reliability, downtime, space requirement, and also cost and so on. You can see that the flexibility are more on PLC. However, for the cost effective, normally control relay is much more cheaper compared to the PLC. Not only that, right now, due to the uh, demand on the integration and so on, some company introduce a PC-based PLC. So in a PC-based PLC, normally we use PC, personal computer, to be our or to act as a soft PLC, PLC that based on software. So this make the integration much more easier compared to use the hard PLC or PLC hardware. So I make a comparison between PC based with the PLC. You can see that some advantage are still on the PLC side, some advantage also has by the PC based controller. Then. Okay, the main critical point of the PC base, even though it's open a lot more of integration, is this kind of PLC or soft PLC, depending on the operating system, which is Windows, Unix, Linux, and so on. And you know that PC somehow tend to crash frequent compared to the PLC. Due to that, it's really there are pros and cons by using PLC and also PC. However, I believe PC is evolved or is improved from time to time, the same as PLC. And I believe one day uh, the difference between PC and PLC it become less and lesser, and then maybe these two will be somehow merged one another. Okay, PLC system, if you can take a look, it consists of power supply, processor module, which is consists of CPU and also memory. input module and output module. In order to program this PLC, we need a programming device, either using a PC or by using some sort of like a programming device like tablet. Okay, each component of PLC, you can see that they has its own function. Power supply to provide voltage, I/O module to provide signal, processor to execute logic, and programming device is to use to program, also memory to contain and also store the logic sequence and also operation. So how to make a connection over the PLC? You have the input. You can see that there's an input module, output module, and inside here there's going to be a CPU and memory. So we make a connection of the input components, input devices into the input module and output component to the output module, and wherever the logics that connect this input and output, relate this input and output, is going to be stored in the CPU, the PLCs. So in the schematic diagram, you can see that we have the three input, which connect, sorry, three input here connected to the input connection, input module, processor is in middle, and output module is connected to the three output component of devices. So each input and output that connected to the PLC is given or is recognized based on the address format. So if we have input, then normally we're going to have I, output O, then depending on the slot number of the PLC. So each input output module, they have a slot. And then the slot number will be given to the address of the component that connected to the slot. And after that, in that slot, normally they're going to have either 8-bit, then each bit is assigned to one input or one output. So for one input that connected to the I12, so we're going to give the address I1, slot 1, bit number 2, output 2, bit number 11. And what happened inside of the PLC? When we run the PLC, it's going to be start, and then you're going to scan the input, the status of the input. Then we'll check with the program scan. Each ladder run, scan, and solve. After that, it's going to change or make changes to the output. And after that, it's going to have some housekeeping, and this process will continue again. All right. So that's some introduction of the PLC. Now we move to the PLC programming. We have learned so far the logic gate and also the sequencing. So now we're going to take a look how we program a PLC based on the knowledge that we have on the logic gate and also sequencing. So in order to program a PLC, we need to define the process to be controlled, draw a sketch of the operation process, including the component involved, determine the sequence of operation to be performed, list the sequence in as much as detail as possible, write in table form, and then after that, write the PLC program for the sequence of operation. So this somehow will help you to program PLC. PLC do not understand the schematic diagram, but most vendors provide software to convert PLC program into machine code, which shield the user from usually having to learn the PLC processor specific code. Translate all the logic into the standard symbol the processor recognize. Terms such as switch, solenoid, relay, bell, motor, and other physical devices are not recognized by PLC. Instead, the PLC only understands input, output, call, contact, timer, counter, and other terms that used normally in the PLC. Okay, remember that I mentioned the different type of PLC, so different brand of PLC, and each brand previously has their own language, the way of program of their PLC. However, there's some standardization happen proposed by the IEC, and IEC is one organization that standardizes electrical and electronic commission aspect. So they decided to have a standardization in terms of programming of the PLC. So the IEC 61131 is proposing 5 types of programming language used in the PLC. The first one is ladder logic diagram. This one, the A. B is the functional block diagram. C is the sequential function chart. Sorry, C is instruction list. And D is structured text, and then the last one, E, is the sequential function chart. If we divided this thing, this 5 programming language into classification, we can see that in PLC programming language, we can do it in terms of textual language, which is the instruction list and structured text, and graphical language, ladder diagram, functional block diagram is sequential function chart. So in the context of this course, we only focus on the step 1 programming language, which is ladder logic diagram. So a diagram in which various logic elements and other components are displayed along horizontal trunks connected on either end to two vertical rails. So you can see that ladder diagram, you have a left power rail, right power rail, and then there's a round in that connected left power rail to right power rail. The power flow is from left to right. And then normally when we program, the ladder diagram, the PLC will read round by round, starting from round 1. After that, we're going to move to round 2, round 3, 4, and so on until the end. Okay, so this is the process of reading the ladder logic diagram. Read the status of all input, store in memory, read the input from memory, and implement the program, storing the output in the memory, and update all the outputs there. So a ladder logic diagram use standard symbol, a shared address to uniquely represent different element and event. 2 vertical bars representing left power rail and right power rail span the entire diagram and are called the power or voltage bus bars. All networks rungs start at the far left power rail, and proceed to the right, ending at right power rail. Power flow from left to right through available closed circuit. So at the left side, normally we're going to write our signal and decision. And the right one is our action. So what kind of symbol that recognized by the ladder diagram? There's a lot of symbol available in the PLC nowadays, but this is the one that we concentrate on this course. The first one is normally open contact. The second one is normally close contact. Third one is output load. The fourth is a timer, and the fifth is our counter. Contact normally is a logic input, like a limit switch for the detector. Output is our load, either motor, light, alarm, solenoid, timer to specify length delay, we divide the counter to count pulses received. So you can see that ladder logic diagram. So input image, output image. So the input we write at the left side for our RAM to check, compare, examine specific condition, and then the output we're going to write at the right side to take some action then. So it will scan from left to right, vertical scanning, and horizontal scanning. So you can see that the output image table is on the status, current state of the input. You read this one, and then after that, you solve the ladder, that program, and then it will transfer the output module. Sorry, it will change the output image table, and then it will send to the output module. Then this is how the ladder diagram is run or performed. So remember, we have learned all the gates from our previous logic gate, logic diagram. Sorry, logic. From our logic gate, and all the logic gate, basic logic gate, and additional logic gate also can be done in PLC. So we can see from here that this one is a AND gate for the ladder diagram. Input A, input B, connected in series, and it's connected to the output. OR gate for the ladder diagram. NOT gate for the ladder diagram is representing by the normally close contact. And then for the NAND gate, it's in parallel. So this is a little bit different than the NAND gate of the logic network of the NAND gate. Logic network diagram for the ladder logic diagram is going to be in parallel. And also for the NOR gate, it's going to be in series there. So maybe you can think why for the NOR gate, even though NOR is the combination of NOT and also OR, if OR is a parallel, why for the NOR it's going to be in series? The same thing as the NAND gate, why if the combination of NOT and AND is N is a series, but for the NAND combination with NOT is going to be in parallel. So this you can try to search by yourself, try to find out why this happened. Right, and also for the ladder diagram, we just try to introduce one more, which is exclusive OR, because some of the system required exclusive OR. Exclusive OR happen if one of the input is 1. If the input is same, either 0 or 1, then the output is going to be 0. So that's how we call it as the exclusive OR. And in ladder logic diagram, we write it as the first one is combination between normally close contact with a normally open contact of another switch, and then we alternate the thing, normally open contact with normally close contact, and we make it in parallel. Then we're going to have the exclusive OR, which is the output is going to be on if one of the input is 1. Okay, the basic point of ladder logic diagram or devices that represent resistive or inductive load to the circuit are shown at the right the diagram. The devices that represent make or break electrical contact are shown in the left of the diagram. Devices connected in parallel with other devices are often called branch. Each complete horizontal line on the horizon of the diagram is typically referred to as a rung. Vertical devices are shown in their normal resting condition. On the shaft state, NC is normally closed and O is normally open. All contact will change when the device is energized. Devices which perform a start function are usually connected in series, while devices that perform a start function are connected in parallel. Rule of thumb of ladder diagram design. So you can see that all input are usually entered as normally open. All output are entered as they appear. Output cord is the last device to be entered on the line. Remember, at the end of the line need to be the output. If overload required, logic relay logic must be entered before the call and as normally open contact. So if you have one output is going to be in one rung, cannot be one output in several rungs. Make sure you combine all the logic and make it in one rung if we have the similar logic or related logic to the output. Okay, so this is sample of the ladder logic diagram. So whenever you actuate the switch, there have some signal appear in our program, and then since it's connected to the output also will energize, and then the lamp will be light up. If we actuated, and we can see that we use the normally closed contact here. If we actuated, then there's no signal appear here, and that's why the output Y1 is not going to be energized, and then the lamp is going to stay dark. So this is some comparison between ladder logic diagram with other languages like hardwire relay control circuit, equivalent instruction list, some example of comparison between functional block diagram and also ladder logic diagram. You can go through that by yourself. This is just for your information. There's also some comparison between the diagram with the instruction list, structured text program, and also screenshot function chart. You can take a look at it. That's some comparison then. Some of the PLC provide the conversion between one program to another one. If you write your program in ladder logic diagram, then you can change directly to sequential function chart, and then it will automatically generate for you there. So this is an example of the operation as simple of operation. Okay, let's take a look as consider a simple process control problem. It's a mixer motor is to be used to automatically stir the liquid in the vat when the temperature and the pressure reach preset value. In addition, direct manual operation of the motor is provided by means of the separate push button. Okay, the process is monitored with temperature and pressure sensor switches that close their respective contact when conditions reach their preset value. So you can see that there's three inputs, manual push button, temperature sensor switch, and pressure sensor switch, and then there's a motor. Output is one. So we would like to steer the motor whenever the temperature and pressure is at the preset value. Or we can also start the motor, steer the motor whenever we push the manual button. So you can see that this is the hardwire diagram, electrical diagram. So in order to do that, we have to make a connection. Input module of the PLC, output module. So we have a 3 input and the 1 output, which is motor. And then after that, we write a program, which is the pressure and temperature need to be reach their preset value in order to energize the motor. Or we can press the manual push button, which also will start the motor. So there's another interactive exercise you can try by yourself. Please, I really request you to practice yourself in order to ensure that you understand the content of the lecture. So this is already an answer for you. You also need to do this exercise. I'm not going to give you the answer directly in the slide. You can try to do it first and then confirm your answer with me. This one, this is also the interactive exercise. This is also interactive exercise. You have 1 week time for you to take a look at the content of the lecture, all 3 lectures, and then you can ask me if you have any question or you would like me to check your answer. This is already the answer for it. Okay, this is also interesting example. You have an answer for it, but you can try by yourself. Okay, then we move to latching. I have introduced latching before. The latch is to hold or maintain a coil and adjust even when the input is not on. So if we have a momentarily push button, we push only once and then after that we release. But since we have a latching, it will memorize our output and then it will remain maintain the output until we press the stop button. As long as the output the relay here is on, then our motor is going to be on. That one is latching. So this is example of latching. So we start press the start button of the motor, and then after that we release. However, since we have output, we take the output value to the parallel of this start button, then it will make the motor latch. So it will keep running until we press the stop. Then we have an internal relay. Internal relay is like act like a relay used to execute the logic of the circuit without having to use a real world output. So we do not have to use the hardwired relay. So we can use the relay inside of the PLC program. Use where an output instruction is required in the program, but no physical connection to a real world device needed. Use with multiple input connection and for starting of multiple output. And also it's used for as a resetting a latch. So this is the control relay we use in order to control 2 input. And also we use as a resetting latch then. Okay, so you can see that push button 1, push button 2 connected to the relay. So the combination of relay 1 and relay 2 is going to energize another relay, and this relay is used in order to energize either the lamp or not. Okay, this is example of the relay. I believe you can go through by yourself. Example of the internal relay. I also give some explanation of it. Stated here the information, the explanation. This interactive exercise. Maybe you can try and take a look at whether you get the output as I mentioned here. And then this is another interactive exercise. You can try by yourself and check the answer with the one that is shown in this figure. And the last 2 items that we're going to discuss is the timer. Timer is have a delay. So timer act as a relay with coil energized after preset time. So they're going to have several parameters like tag name, preset, accumulator, enable bit, and then we're going to have a timer timing bit, done bit. So in order to set a timer, we have to make sure that we put the parameter correctly, and then the timer. Okay, this is the tag name, and then we set the preset value. Whenever the input sent to the timer, the end bit will be energized, but the done bit is still waiting for the value turns or reach the preset value. So after you reach preset value, then the done signal will be energized then. So in the PLC, the real PLC, you have to use based on the PLC programming, but for simplify in the writing of some program based on the question or whatever. Uh, if you would like to write timer in your ladder logic diagram, then you can just use the simplified version of the timer, which is you give a name of the timer T000 and the numbers of preset value, and then you make a connection the timer with the output. Okay, so this is example of the timer. You can go through also by yourself. I believe it's self-explanatory. Self-explain. I already put some indication what you have to know and what you have to understand. So this is all the example, timer on delay. Okay, the timer, they have two types, timer on delay and timer off delay. So the explanation of that is given. Okay, this is interactive exercise of the timer on delay. This is also the interactive exercise, the explanation of interactive exercise for timer on delay. And then we have a timer off delay. Okay, the difference between timer on delay is timing, timer on delay, timing to turn on something. Meanwhile, timer off delay, after the input is off, then it will wait for certain delay, and after that, it's going to energize. Sorry, whenever the input is on, the output is immediately on, but when the input is off, there's a time delay, and within the time delay, the output is still on, and it will off when it reach the specific time delay. Okay, and there's an example of it. You can go through by yourself, I believe. And there's also a combination of timer on delay and timer off delay. And the explanation of the exercise time. And the last one, the last component of the PLC that you need to know is the counter. Similar to the timer, except for the counter is the count change in state, or the change of on and off, or 0 to 1, and it can count specific number of contact operation. There's a two type also for counter down counter and also up counter. Count up CPU counter will cause the accumulated count to increase by 1 every time. Meanwhile, count down counter will cause the accumulated count to decrease instead of increase by 1 every time. It's a false true. So counter also there's parameters that need to be defined, like a preset, accumulative count value, accumulated value, count out bit, count down bit, done bit. So this is an example of it. You can go through by yourself. I believe your level, the master level student, already able to understand by yourself. In case you need some explanation, please don't hesitate to contact me. Interactive exercise, I already give some explanation of it. And just for the good information, even though some PLC only cover digital input output, however, it's possible to have to control the analog input output by having the converter, analog to digital to analog converter, and analog to digital converter. And nowadays, PLC also there's a special module that cover for input, for analog input and output. Okay. Okay, there's at the end of the slide, I prepared some interactive example, so you can take a look at it. There are two interactive example how to program automatic stacking, and also, so this is the last example, I believe, and the rest is the tutorial. You can try to do by your own again, and then confirm with me your answer. They have a tutorial 1, tutorial 2, tutorial 3, and tutorial 4, and that's it. Okay, please make sure that you practice yourself. PLC is not as some other topic. You need to practice in order to make sure that you understand. It's somehow like programming. If you're not practicing your programming language, then you're going to forget, so you're not able to answer when there's a question in the exam or the test. As a summary, you have to know the process, flowchart, how to come up with a related diagram, either to have the proper sequence of operation. After that, you can create a Boolean equation, control relay, and from there you can write your related diagram. Okay, that's all for this topic. I believe I already covered all the 3 topics. Once again, I advise you to try to do the exercise. And the exercise, try to do the tutorial, and then you can come to me if you have any question, and also you would like to have some confirmation or check your tutorial or exercise then. Thank you so much then for your attention. Thank you for your participation. I wish you all the best in your study, and don't hesitate to contact me if anything. Thank you. Assalamualaikum warahmatullahi taala wabarakatuh.